Hi, I wanted to show you a quick overview of the convex schema parser, especially how it is used and supposed to be integrated. So what we have here is just a repository, which is also linked in the video description. And we provide an example project, which looks like this. So you have the convex example, which defines a simple schema as an example instruction MIME type and a schema for messages and assets, as well as actions or a mutation and a query. These are public and they live in this namespace. We can also take a look at the convex dashboard. And yeah, I mean, as you might already know, they are prefixed with a specific name that you would pass as a string to the convex client to issue calls. And for Rust, you would create a B-tree map, encode your types, hope that they fit nicely, and almost the same for Python. So it was a hassle for us to think about the fact that we have multiple repositories, multiple projects, multiple clients which talk to the same convex schema, or convex DB, I should say. And instead of maintaining all of that by hand, we created a type gen which creates more or less thin type gen wrappers around the convex clients that are available for Python and Rust so far. Other language could be also integrated if there are convex clients available. And I just want to show you what has to be done and how we use it for our use case. So yeah, as said, we have this convex example of this pretty simple convex project. We have two Python clients here which use the generated API, and as well as a Rust client. And now I will just show you what the convex schema parser does. So when you have everything set up, so just go in here and convex schema parser dev. That's what I would do. So then it checks if then it checks the convex schema in the convex backend that we have right here, and it also generates the types for all your functions, and then it scans the generated type declarations to provide typed functions with all the encoding enabled or handled for you. For Python, we also use Pydantic. Right now, the Python client or the generated API is called Puppy. You will see in a second how this is handled. And yeah, we have some simple wrappers. We use Pydantic under the hood, so we can make sure that the validation is handled and you're being notified if there might be any problems. And let's see, we have a messages doc, so basically the type of the document for messages, type of the document for assets, as well as the API itself, which uses convex's naming convention. So if convex expects list messages list as the function prefix that you would call, you would also get the members in your API client. So as soon as you understand how convex handles all the naming, it's pretty intuitive to know how the API calls look. So for instance, if we now take a look again at the Python client, we have the convex client initiated, pass it to the generated API, which uses the client then. And yeah, then we have the member list messages and the public function that is exposed list, as well as send messages and send. For the Python case, we enforce named arguments because since we parse the type declarations generated by TSD, it might be that the arguments of the functions are reordered in some kind of way. If you then imagine that you use strings in 4 parameters and they suddenly get changed in the ordering, you wouldn't be notified. So we enforce this in Python to keep everything safe, especially with generated code. For Rust, we have a similar approach. Since Rust does not support named arguments, we create a arg object for your API functions. So there is also no issues there if anything gets reordered, and you can always be sure that the author stays an author, the body stays the body, no matter how or whatever TSC does in the background, which is important. Good. So far so good. This is basically all there is. A simple interface for everything. Now we'll go a little bit into the setup that's required, because the convex-schema-parser, when you have it installed, needs to know where is your convex project living. So right now I executed the convex-schema-parser in the example folder, and okay, no, maybe not 3. Let's take a look here. We have the convex example here. This is our convex project, Python client 1, 2, Rust client, and so on. There's a convex parser YAML, which is the configuration file that I've opened here, and it points to the convex example. It then points to some sort of declarations directory and a validation path. The validation path is optional. It's just because we want to make sure to only output code that also compiles and works, and give you a hint if maybe we did something wrong, or if for some reason you were able to break something in your convex definitions. And by default, this is your home directory. And all that does is convex-schema-parser Rust validation project. It just sets up a very a sandbox small project for Rust, which calls cargo check and stuff. We have the same for Python. It's not currently enabled, but it will be. And the same will hold true for any other languages we might support. The interesting part now is, okay, where's the generated code? Where's the generated code moved to? And for Python and Rust, it's pretty easy. So Python just allows you to have extra modules, and you can access them by name. I could also call this, I don't know, generated API for Python client 1. And if we call this again and go into Python client 1, we would have to change this to generated API, just like here, and then it would work again. For Rust, it's a little bit more involved, since you have to announce generate your module in your main file. But I mean, the same holds here. It's pretty easy then. Okay. So far so good regarding this. What is up with this declarations directory? Since the schema parser has to generate the type declarations, we have one thing that we force upon you, which is the tsconfig declarations.js. You can write it however you want to, and the thing is, the out directory you specify here is we have to know about it, or the convex-schema-parser has to know about it. That's why right here we point to the path of the temp declarations, where TSC will move all the generated declarations files. And the final thing is, your top level package JSON needs this set of scripts, because we call npm or pmpm run declarations on your project, and then it just gets generated everything here. If you issue if you issue convex-schema-parser init, it will also tell you about it. so what has to be done. And finally, it also generated a convex-parser YAML. It also generated an example configuration, which you can adapt to your liking. Then some more comments. The same holds true for our README. It hopefully contains everything that you need to know. The final thing is it's written in Haskell, so to install it, the easiest way to install it is to have GHC up installed together with Cabal and a GHC version higher than 9.10. And yeah, okay, that's all. Thank you.